All right, so here in the second part of Unit 4, Section 1, we're still looking at single sample proportions, making inferences on the population proportion. But now, instead of using a confidence interval, we're going to talk about how we can do a significance test, also known as a hypothesis test. So starting out, of course, we have to make sure that some conditions are met. The conditions that have to be met for a hypothesis test for a single population proportion are the exact same as they were for the confidence intervals in the first part of this section. So the first condition, which we always have for any kind of inference, is we need to make sure we have a random sample and there's no bias occurring. After that, we want to make sure we have a binomial setting. And whenever we are taking a sample, we never truly have an actual binomial setting. That's because when we're taking a sample, we're removing subjects from the population. And when you remove subjects from a population, the proportion changes. So, in order to make sure that our proportion doesn't change too much, we want to make sure our population is very large compared to the sample we're taking. In other words, if our population is really, really, really big in compared to the sample we're taking, then the proportion changes when we remove that sample will be so minuscule that it really won't make a difference. So the rule of thumb for that, we've said it lots of times before, is that the population size, capital N, needs to be at least 10 times greater than the sample size. If that is true, then we have a good binomial setting. Then, with binomial settings, we prefer to calculate our probabilities in binomial settings using normal approximation. And as we've seen in other units, as well as the last section, in order to use normal approximation, we have to ensure that the number of successes as well as the number of failures in our sample is at least 10. If those two criteria, that last part, is not met, then we can still do this, but we would have to use exact binomial probability, just like we did in the previous unit. Okay, so let's go ahead and remind ourselves how we construct a confidence interval for a single sample proportion, and then we'll move on and talk about the hypothesis test. As you know, a two-sided hypothesis test can give us the same conclusion as a confidence interval. So in this one, it says, let's construct a 95% confidence interval for the proportion of Americans who say apples are their favorite fruit. We'll use a sample of 66 out of 595 Americans. Okay, so first thing we have to do is check our conditions. Is this a random sample? Yes. Second, is this a binomial setting? Our sample size here is 595. Is it accurate to say that the population of all adult Americans is at least 10 times greater than 595? Or is the population of America greater than 5,950? Yes, it is. So we have a binomial setting. Second, or third, in order to use normal approximation now, which we prefer, in this binomial setting, we need the number of successes, n p hat, to be greater than or equal to 10. Here, our number of successes is 66. Oops, equals 66. And 66, of course, is definitely greater than 10. And we need our number of failures, n times 1 minus p hat, to also be greater than 10. Well, if there's 595 Americans and 66 of them said yes, that means the other 529 said no. That is 595 minus 66, which of course is definitely greater than 10. Now that we've checked our conditions, we can go ahead and start constructing our confidence interval. So from the last part of this section, we learned that a confidence interval for a single separate proportion is always our estimate, which in this case is p hat, plus or minus our critical value, which is going to be a z-star value because we're using normal approximation, times the standard error of the proportion, which we use this formula to find. Okay, so now we just need to plug in the correct values, starting with p hat. So I, of course, talked about the number of successes above here without actually identifying p hat, because n times p hat we know is the number of successes. It's just a formula that helps us get there if we're not given that actual number. So to calculate p hat, since it's not given to us explicitly, we take the number of successes, that's 66 there, and divide it by the sample size, 595. So 66 over 595 gives us a sample proportion of 0.11. Okay, the next thing I need here to put into this formula is my Z star. And since we're doing a 95% confidence interval, Z star is always going to be 1.96. And then lastly, of course, N, we already identified N, the sample size was 595. So let's plug that all in and we will have our confidence interval. So P hat plus or minus Z star, and then we have a square root bar, P hat in the numerator, 1 minus P hat, 1 minus 0.11 is 0.89, and N in our denominator. So I can then grab out my calculator, multiply on the top the 0.11 times the 0.89 to start, following our order of operations, and then divide by the 595, and then square root that whole thing to get our standard error, and then multiply that by our critical Z value, 1.96. So we get our margin of error is 0.025. And then I just add and subtract to get my lower bound, which is 0.085, add to get my upper bound, which is 0.135. And we're done. This is my 95% confidence interval, which again, that means that we are 95% confident that the true population proportion of Americans who say their favorite fruit is apples is somewhere within this range. Okay, so now let's move on and talk about doing a hypothesis test or a significance test instead. So the first thing we just saw in that last example that we use this notation to calculate the standard error of the proportion in our confidence interval. Okay, it was part of what we wrote above. When we're doing hypothesis tests though, it looks a little bit different. As you can see, it's basically the exact same thing. One has p hats, which indicates the sample proportion. The other has these p with a subscript 0. We call that p naught. P naught is the hypothesized value. So when we're doing hypothesis tests, our standard deviation is going to be calculated not using a sample proportion, but using a hypothesized proportion. Okay, so let me show you how that works. So I have this here, this example they did in Apex, and I kind of split it up step by step. We're always going to follow these steps when we're doing these hypothesis tests, and really any type of hypothesis test. We just have different types. We always start by checking the conditions, and then we state our hypotheses in context of the problem, state the test we're going to use as well as the significance level, compute your test statistic and your p-value, and then state your conclusion in context of the problem. Every time. So here it says we'd like to determine the proportion of the people who say apples is their favorite fruit. We have to see if that decreased from 1998 to 1999. So we're looking at the exact same information we saw in that last part. So to do this, we're going to conduct a one-sided hypothesis test. And that just means our alternative hypothesis is going to be either a less than or a greater than hypothesis. A two-sided hypothesis is where we have that our alternative hypothesis is like a not equal to situation. Okay, so first thing we have to do is check our conditions. We actually did that on the last page. We checked and made sure that we had a random sample. We made sure we had a good binomial setting, meaning the population size was at least 10 times larger than the sample size. And we checked that we could appropriately use normal approximation by checking to make sure the number of successes and the number of failures were both great, at least 10. Okay, so we did that on the last example. So I'll put a note here, see last example. Okay, so now let's move on to the actual hypothesis testing. So the first thing we do, of course, or second thing now, I guess, is state our hypotheses. One is the null hypothesis. The other is our alternative hypothesis. So the null hypothesis is always going to be that nothing has changed, nothing is out of the ordinary. So we would say our null hypothesis in this case is that the population proportion, P, no subscripts or hats or anything, the P by itself is the population proportion, and that's what we're trying to make an inference about. So our null hypothesis is nothing changed from 98 to 99. So the proportion of people who preferred apples in 99 will be the same as it was in 98, which is, and actually, they didn't give us information on here. It does say in 1998 in Apex, it says that that population proportion was already known to be 0.16. Okay, so that's kind of important. So in 1998, the population proportion was 0.16. We are going to say our null hypothesis is that has not changed. And now that it's 1999, the population proportion is still 0.16. Okay, and then my alternative hypothesis, I should write this in context first, huh? The proportion of people whose favorite fruit is apples has not changed. Okay, so it's still 0.16. And we're told now to do a one-sided hypothesis test, which means my alternative hypothesis is going to be that the population proportion is either greater than 0.16 or it's less than 0.16. So let's see, what are we trying to say here? Are we trying to see if this proportion has decreased or if it has increased? Again, they didn't write this out so much as like kind of say it out loud. They are believing in this case that the number of people who say their favorite fruit is apples has actually, oh, there it is, decreased. There it is, decreased. Okay, so it would be a less than one-sided test. So I'll write that in context. The proportion of people whose favorite fruit is apples decreased from 98 to 99. Okay. All right, so now that we've got our conditions met, we've stated our hypothesis in context of the problem, we now need to tell which type of test we're going to do and the significance level that we're choosing to do it at. So we are looking at proportions here, and we have one sample, and we have already decided that we can use normal approximation, which means we're going to do a z-test. So I will state, we will use we will perform, I should say, or perform a one sample z-test for proportions. At significance level alpha, and we'll choose 0.05 here, just like we usually do most of the time. Okay, so now that we have that stated, we can go ahead and compute our test statistic. So here's the formula here for computing a test statistic for a one sample z-test for proportions. Remember, when we're calculating a z-test statistic, we're basically just standardizing our estimate. It's always our estimate minus our hypothesized value over the standard deviation. So for proportions, our estimate is p hat. Our hypothesized value will be p naught, and our standard deviation is this here that we had on the last page. So let's plug all this stuff in. So actually, first of all, I'll go ahead and do this. P hat, what is our observed value? So this is referring to the sample that we talked about in the first part of this problem. P hat, we already calculated beforehand, was 0.11. That's from a random sample taken of American adults in 1999. P naught is our hypothesized value, meaning I go up here to part 2 and look at what did I say H naught was. I said H naught was 0.16. That's the true population proportion from 1998. Okay, so those are not the same numbers. Okay, also we need N here. The sample size when we calculated this p hat on the last page was 595. And that's it, that's all we need. So let's plug those in and see what we get. Z equals p hat minus p naught over the square root of p naught times 1 minus p naught, which is 0.84, all over n and square rooted. So then we pull out our calculator and start putting in buttons, make sure we follow our order of operations. On the numerator, 0.11 minus 0.16 is a negative 0.05. And in the denominator, when I simplify that, we should get 0.015. So then we divide to get our test statistic, negative 3.33. Okay, so that is our test statistic, which we can use then to calculate our p-value. So our p-value, remember, is the probability that that z-score, the probability that our alternative hypothesis is true. So we just found our test statistic was that z was negative 3.33. And now I need to decide, what am I going to look at? So I go back up to my alternative hypothesis. My alternative hypothesis was a less than statement. So we're calculating the p-value then, that z is less than negative 3.33. Okay, so I can go ahead and use my calculator to do this, normal CDF. It is a z-score, so my mean would be 0, my standard deviation would be 1. Or of course, what we would usually do in this case is just use our standard normal table, which will be provided during our AP exam. So I go to my standard normal table real quick. We're looking at below negative 3.33. We got lots of marks on here. Let's clean it up a little bit. So here's negative 3.33 right here. And double checking, yes, our table does show us the probability below, not above, so we don't have to subtract from 1. So the answer is simply 0.0004, or p-value, I should say, is 0.0004. So again, if you were to use your calculator and the normal CDF, you should get the exact same answer. Let's go ahead and just check. So I'll go on distribution menu, second bars, normal CDF. We want less than negative 0.333. So starting at a very negative number, upper bound would be negative 3.33. And this is standardized. So our mean is 0. Our standard deviation is 1. Paste. And there we go, exact same answer. This is scientific notation, which means we would move this decimal place 4 places to the left, which gives us 0.0004. All right, lastly, we can make our conclusion now. So remember, we always compare this p-value when we're done to our alpha we chose here, 0.05. If our p-value is less than alpha, we reject our null. If our p-value is not less than alpha, we cannot reject our null. So we can definitely say that our p-value is less than alpha. Since our p-value, and I'll write the actual number, 0.0004, is less than our significance level, alpha is 0.05, we reject the null. And then we have to state, what does that mean in context? Okay, if we reject our null, then that means we are supporting our alternative hypothesis. So I can read it right here. The proportion of people whose favorite fruit is apples decreased from 98 to 99. The proportion of people whose favorite fruit is apples did decrease from 98 to 99. So that's another handy thing about writing your hypothesis in context at the beginning is when you go to state your conclusion, you're basically just going to write one or the two of these two sentences that you wrote up in step 2 as part of your conclusion. So you don't have to think too hard about it. All right, let's do one more of these. This time, let's do a two-sided hypothesis test. Remember, two-sided just means that my alternative hypothesis is going to be that my population proportion does not equal the number I say it does in my null hypothesis. Okay, which when I say it's not equal to, that means it could be less than, or it could be greater than. That's why we call it two-sided. So here it says, suppose the research and development department of Wagging Tail's dog toy company has developed two chewy toys for dogs called Chew Yum and Gnaw Fun. They want to see which one dogs prefer. They select a random sample of 100 dogs and present each with both toys. The researchers keep track of which toy each dog prefers. Here are the results. Chew Yum 56, Gnaw Fun 44. So step 1, we got to check the conditions to make sure that we can do this. So first one, do we have a random sample? Yes, we do have a random sample. Oops. Okay. So we have a random sample. And is it from a binomial setting? That's my second condition. If it's from a binomial setting, then our population size needs to be at least 10 times bigger than our sample size, which is 100. So 10 times 100 is 1,000. Is there more than 1,000 dogs? It doesn't say for a specific area, so I think we're just saying dogs in general. Is it reasonable to say, they don't give us an actual population number, so is it reasonable to say that there are more than 1,000 dogs in the world? Absolutely. So binomial setting. Okay, which is all good. Now, if we want to be able to use normal approximation in this binomial setting, though, we have to check our NPs and n times 1 minus p's. In other words, our number of successes and our number of failures. Okay, so let's, first of all, we got to figure out what is a success here. They don't necessarily say. They just give us the answers Chew Yum and Gnaw Fun. Let's see. Yep, I don't see anything there. Okay, so we could actually choose either way. Because since we're doing a two-sided test, either Chew Yum's going to be more than Gnaw Fun, or Gnaw Fun's going to be more than Chew Yum, which means Chew Yum is less than Gnaw Fun. So since we are doing a two-sided test, we could actually choose either event to be our success, and we will get the same results. Only works that way with a two-sided test, though. So in Apex, they chose Chew Yum to be their success, by the way. So we're going to say let a success in this binomial setting be that Chew Yum was the chosen dog toy. That means our NP hat, our number of successes, was 56, and our N times 1 minus P hat, or the number of failures, was 44. Both of those numbers are greater than 10, so we can use normal approximation. All right, conditions checked, moving on. Let's state our hypotheses. So our first hypothesis is our null hypothesis. Okay, and here our null hypothesis would be that the dogs don't prefer a specific toy, which would mean that they prefer Chew Yum and Na Fun equally. So it'd be a 50-50. If that's not true, then that would mean the dogs prefer one of the two toys over the other, so the proportion would not be 50-50. Okay, so I have to write that in context. If the proportion is 0.5, we are saying the dogs have no preference. Have no toy preference. Or no significant toy preference, right? And of course, if that's not true, that would mean the dogs do have a significant toy preference. Okay. All right, which brings us to step 3. Let's go ahead and state the type of test we're going to do. We have one sample, we're looking at proportions, and we said we could use normal approximation, which means we're doing a z-test. Oops. And while I state my test, I also want to state my significance level. And big surprise, our significance level is going to again be 0.05. So let's compute our test statistic. Just like last time, we're using the exact same formula. Z equals P hat minus P naught over the standard error or standard deviation, which is P naught times 1 minus P naught over N. So starting with P hat, what is P hat? The number of successes over our sample size. We had 56 successes out of 100, that's 0.56. N, our sample size, was 100 dogs. P naught, our hypothesized proportion, H naught, was that P was 0.5. So let's plug those in. 0.56 minus 0.5 over the square root of 0.5 times 0.5, 1 minus 0.5 is 0.5, over 100. And we end up with, in the numerator, 0.06. In the denominator, that simplifies to 0.05, which is 1.2. So our test statistic, Z, is 1.2. Now to calculate the probability, the p-value, we find the probability that Z is not 1.2. And again, I chose a not equal to symbol because that's the symbol we've used in our alternative hypothesis. Okay, so again, I could go ahead and use my calculator to do this, normal CDF, or I can go ahead and use my standard normal table. Okay, this is a two-sided test. So this is the same thing as saying, in our standard normal table, or standard normal distribution, Z distribution, our mean is always 0. And our standard deviations are 1. So 1.2 is somewhere about here. So this shaded area would represent the probability that Z is greater than 1.2. And we want a two-sided test. And since our z is proportional, that would mean this over here is a negative 1.2. But again, these two tails have the exact same area. So the easiest way to do this maybe is just to find one of these two tail areas, one of these two probabilities, and then just multiply it by 2. I could choose to find the two probabilities separately and then add them together as well, but it would be more work. They really are the same area, the same probability, so it's easier to find one and then multiply by 2. If I want to use my table here, I'd probably choose this one. Remember, your standard normal table only shows you the probabilities or the areas below a certain number, not above. So I'm going to go ahead and find the probability that z is below a negative 1.2 from my table, and then just multiply that probability by 2 so that I have both ends. So I'll go here to my z table, negative 1.2. Again, I have lots of other marks in here. Clean it up real quick. Negative 1.2 is right here. So the probability that z is below negative 1.2 is 0.1151. So I multiply that by 2, so I have both sides, and that gives me 0.2302. And we are done. So what is our conclusion? Well, remember, we chose a significance level of 0.05. Our p-value has to be less than that to reject our null. 0.2302 is not less than 0.05. So since our p-value (0.2302) is not less than our significance level, alpha 0.05, we fail to reject our null hypothesis. Okay, that does not mean we accept our null. Remember, we never accept our null. If we fail to reject our null hypothesis, that means that we do not have enough evidence to accept the alternative. We do not have enough evidence to decide if dogs prefer one toy over the other. Okay, and that is that. So the last thing we have on here is, well, what if we wanted to use our calculator to make this whole thing a whole lot faster? So in your calculator, under the test menu on your stat button, you have the option to do a one sample proportion z-test. So I'll show you where that is here. On, clear, super straightforward. You click the stat button, move over to tests. Remember, all of our hypothesis tests and intervals of all different types are right here in this menu. We're right now doing a one sample z-test for proportions. So I look for the one that says one sample z-test, not z-interval, with the word proportions in there. It's my option 5. And it asks me for the information that I need. So I can go ahead and apply this to, let's see, there you can see on here, they're looking at the apple scenario where P naught, our hypothesized value, was the proportion of people who preferred apples in 1998.16. Our number of successes in our sample was 66 out of 595. And we did a one-sided test where we were trying to see if that proportion had decreased in a year. So when I hit calculate, it gives me that, again, just like before with all of these we've done, it gives me the test statistic.
Ms. Bannon,
It gives me my p-value, and p-value right here, and then I can go ahead and make my conclusion that way. So going back, clear, I can go ahead and do the same thing for the dog toy thing we just did. So I'll go down here, choose option 5, one sample proportion z-test. And our last example up here, and kind of go back to where we were. Here's all our information. I can say, okay, our P naught was that there was no preference, so 0.5. Our number of successes we choose Chu-Yum was 56 out of 100. Oops. And we did a two-sided test here, so I choose the not equal to and calculate. And there we go. There's our test statistic 1.2 and our p-value 0.23. Exactly what we had before, and then we can go ahead and make our conclusion. So that's it for Unit 1.